Well, you want to start, Mr. Rott?
Yeah, okay, so what we're going to be doing here is we're going to get back to greatest common factors, which is where we try to find out what is the term that each term in, for example, a binomial or a trinomial would have. So how would you define a greatest common factor, Mr. Elliott?
Just kind of based on the words, we know that factor implies multiplication, whereas term implies addition. So we're looking for something that we could multiply, or that has been multiplied into this particular binomial. Like if we look at number 1, we're looking at the two terms and saying what is the largest possible number that we could multiply, or that has been multiplied into both of those.
Oh, I see. Okay.
How would you say?
Well, I'm looking at that 3x plus 3y, and I notice that the x and the y are different, but the 3 is the same for both of those. So it's almost as if I've taken an x and multiplied it by 3, and I've taken a y and I've multiplied it by 3. So I'd say that both of those terms have been multiplied by 3.
So when it says factor, this is factor, verb. I always joke with this, verb, transitive, because you're factoring an object.
That makes sense.
A direct object. So because it's a transitive verb and you're factoring it implies that it wants you to do something. So instead of just saying factor, we can also say express as a product.
Express as a product. I like that. So instead of having 3x plus 3y, we're going to have something times something.
Right.
That's going to be identical to that.
And that's going to be true in the entire chapter. We want to express everything as products, everything as something times something. While it's true that some of the factors themselves, the noun factors, may include plus signs, we don't want to have any plus signs in between our factors. They all need to be multiplied. So you just said that 3x plus 3y has a 3 in common. If we were to factor out a 3, we'd be left with...
Well, let's see. If we were to... This would almost be like undistributing, wouldn't it?
Yeah, it's the distributive property in reverse. We're pulling the 3 out.
So if we pull the 3 out, then what would be inside would just be an x and a y. And when I mean and, of course, that means plus. And then we could check that and say, well, if we distribute that 3 back through, we should get 3x plus 3y, and we do. So by factoring this, we see that what we end up with is 3 times the factor x plus y.
Now sometimes I'll ask the question, how many factors or how many prime factors are we left with? The 3 itself is prime, and I'm going to erase some of this pink because our answer really is the 3 times x plus y. We never really express the 3 in its parentheses of its own. However, if we did, we'd see that we just have a 3 and then an x plus y, and there's an invisible time symbol in between there, which means that we're left with 2 prime factors. I couldn't take the 3 down anymore. I can't take the x plus y down anymore.
That's an excellent point, yeah.
So let's continue to the next one. I sometimes start by putting parentheses around to see it as a binomial.
Mm-hmm.
Right now it's one factor. Can we make it multiple factors? Just like if I were to take a number like, let's take 169 and try to factor that, I'd be looking for numbers that multiply into 169, and the only one is 13 times 13. But I just took one factor and I made it 2 factors, but they're smaller factors.
Okay.
So this, 13x minus 13, can I make it smaller factors?
Almost as if you were to put the 13x minus 13 where the 169 would be at the top of your tree.
Yep.
And then see if you can't split that into parts.
So what divides 13x minus 13?
Well, let's see. If I was to look for something that divided everything in that binomial, I would think that 13 would go.
When you divide that through, you get...
Let's see. It would be 13x divided by 13 would just be x. And then we have minus 13 divided by 13, so that would be minus 1.
And 13 times x minus 1. Now, we're never going to show it as a factor tree like this. You certainly can. But really, you're just going to get a habit of what we've been calling undistributing, pulling the 13 out and leaving it as an x minus 1.
Yeah, that's a lot simpler. And eventually, and would you agree, Mr. Elliott, eventually what you're want to get to is to be able to look at this and get a sense for being able to recognize what factors are present. And that just takes a lot of practice. So fortunately, we have a lot of practice here for you.
And we do. In fact, at any time in this video, if you want to pause and kind of work ahead on a few of these and come back and check your answers, you're certainly welcome to.
Absolutely.
I think that's one of the advantages of doing this. But we'll walk through some of these and start to move a little bit faster. We can see in number 3, we don't just have constants that are the same number, but I'm sure if you looked at 24 and 12, you could find a large number that multiplies into both 24 and 12.
I'm going to guess it's not 1 billion.
It's not 1 billion.
Okay.
But it's probably not 2.
No, 2, I think we could find something bigger than 2. 12?
12. 12 divides 12. It's the largest number that divides 12, and 12 divides 24. So if we pulled a 12 out and divided 24x by 12.
Let's see. 24x divided by 12 would just be 2 x's.
And then minus 12 divided by 12
would be
1.
Yeah.
And it's important to remember that a number divided by itself is 1, and we still have that minus 1. You don't just lose that and make that a 0.
Right.
The other interesting thing about this is that if you ask the question, how many prime factors do you have, which is something interesting to kind of examine, we'd have to look at 12 and break that down even further to see how many prime factors. It's a little bit besides the point with factoring, but it's important to see that the 2x minus 1, the polynomial part, we can't take down any further. So this is why, in the math sense, this is considered factored.
Because 2x and 1 don't have any common factors.
Correct. Okay, you want to write a little bit since I have bad handwriting?
Yeah, that sounds great. Okay, so we're looking at xy minus 3x squared. We need to find some factor that is common with both of those. And looking at this, I notice that this first part just has x times y. So I'm guessing that whatever factor I'm going to be looking at, it's going to have to be either an x or a y, because otherwise there's nothing else that this factors into. Would you agree?
Correct.
So if I look at the second term, I would notice that this only has x's in it. So my first inclination would be to say, and I think we've been doing this in this lovely orange color here, is that x would be the factor that I'm going to undistribute. And then what do you suppose we'd have on the inside?
Well, xy divided by x is just y. And then we learned that 3x squared divided by x means that we divide, we subtract our exponents, or basically we just lose an x. And so we now have just 3x. This would be a good one to mentally check when you multiply it back out. Do you get the original polynomial, xy minus 3x squared? Yep.
Yeah, and we can check that. If we just do our distribution here, we get x times y, which is xy, and then minus 3x times x, and by now you should hopefully be able to say that that is minus 3x squared. So this is definitely the correct answer here.
And number 5 is a little bit interesting because with number 5 we have a 19 and a 6. I mean, obviously they don't have an a in common, so we can't look at that. 19 brings us to our discussion of what a prime number is. A number that doesn't have any factors other than itself and 1, or probably more appropriately a number that is itself the expression of its unique product of primes. It's getting a little bit more terminology than we probably need at this point. I know that when you learn prime numbers, you learn that it's a number that can't be expressed as a product of anything except for itself and 1.
Right.
That's what 19 is. So if you look at the directions at the top, it says, if not factorable, write prime. And then it follows and says that there are 2 prime polynomials. I think we've just found one.
Yeah, I believe you're right, because this 19 and this 6 would be the only things that we could possibly factor, and 19 and 6 don't have any common factors. So I believe we would probably just write prime here.
Sure. And again, something that I think is helpful, if you put parentheses around the polynomial or just kind of on the sides, it's another way to sort of express that we have a prime factor, because it's still one factor that could be multiplied by something later if we needed it to. But if we're looking for factors, it's its own factor, just like a prime number would be its own factor.
Sure, okay. So when we say prime, we could either say that this thing in parentheses is its own factor, and there's nothing else. Or another way to look at it would be to say that there are no terms or no common factors in these terms.
Yep.
So there are no common factors of 19 and 6a. You don't have to write that. Prime pretty much says that for us.
Yes. So number 6, we look at the 4x and the 6y. Obviously the x and the y don't have anything in common. The 4 and the 6, you know, you can take out a 2. So let's just go ahead and take out a 2 and see what's left.
Okay, well let's see. When we take out the 2 from 4x, we should be ending up with 2x. And if we take that out from minus 6y, we should end up with minus 3y.
Yeah. Sometimes you can do, like in number 7, a little bit of trial and error. This one's a little bit more simple. But if we look at number 7. We have 36 and 8. And just think, if I took out a 2, would that be big enough? Well,
That's a good question. When we're left with that, what would we have on the inside? We would have 18t minus 4.
but then we could keep taking out another 2.
Oh, yeah, you're right, because 18 and 4 are both even numbers. So if we take out another 2,
we have 2 times 2, and then our 18 changes to a 9, and our 4 changes to a 2. And we just divide it through by another 2. So if you look back at the original one, we could have taken out a 4. But if you didn't see that, that's okay. You at least got to the correct result of 4 times 9t minus 2.
and that's how we would write it. We wouldn't keep it as 2 times 9t minus 2.
No, the convention is to write it as the product 4.
So that we have just one coefficient.
Yeah. And some of that is us. We just want you guys writing it all the same way. I've had students express it as 2 squared, and I don't cry about it, but typically I think they think it's easier just to write it as a 4, and that's fine.
Sure.
Okay, number 8, we start looking at coefficients and variables. Our 21 and 35 both share, I think you could see they share a 7 in common, but they also, 21c and 35c squared, the largest power of c that's present in both of those terms is the c to the first power. So we can pull out a 7 and a c. And Mr. Rott's writing on top of these the prime factorization of each of these different terms. And so you can sort of look and see what do they have in common. They have a 7.
So they both have a 7 in their factorizations,
Yeah.
and they both have a c in
And
their
they both have a c.
factorizations. So if I take out the 7 and the c, then this first one would be left with just a 3.
Right.
And if I take out a 7 and a c from the second one, I'd be left with just 5c.
Yep. And the plus sign carries from the previous binomial. So again, if you were to multiply that back in, you'd see it, and you'd be okay. 19, number 9. Think about this. We're going to get problems like this much later in the chapter too, and you're going to have to look and remember that the very first thing you always do is look to see if they have any common factors among all the terms.
That's a good point.
And
yeah.
one of the tricks is to look at what the limiting one might be. You see some m's, but if we go all the way to the right, we just see a plus 9.
Yeah.
So we know the m's won't be included in anything.
Yeah, we can't take an m out of every term, in other words, right?
And the largest number we could include would be the 9, and in fact 9 divides all 3 of those.
So we could take the 9 out?
Pull the 9 out, and you're probably going to be done.
Okay, well, let's see what would we end up with. We'd have n cubed minus 2m plus 1.
Yep. And that plus 1 is very important. See the pen?
Yes.
We don't want to ever forget that when we take a number like this and divide it by itself, we're still going to end up with a plus 1. That's a very common place that people can forget to write that, and certainly you guys won't. Okay, you might have to deal with my bad handwriting, but let's change it up a little bit.
Absolutely.
So we go 14x squared, 22x cubed y. Let's look at the 14 and the 22. Constants first. Largest power. 14 is 7 and 2, but 22 is not 21, so I think we're just stuck dividing a 2 out of there.
Yeah, because 22 is 11 and 2. So we have a 7 and 2 and an 11 and 2, so they both have a 2 in common.
Now, instead of kind of writing this whole thing, let's look at the variables. They both share x's, and this is an x squared, this is an x cubed.
Oh.
The biggest power that both of them have in common would be a square. We want to take 2 x's out because we can, but we can't take 3 x's out because the first term doesn't have 3 x's to take out. So if we pull out an x squared, now we have to do a little division, and this goes back to section 5.2 where you guys were dividing polynomials. We're saying, okay, we're taking out the 2, we're taking out the x squared. What's left? If we look at what's left, we just have a 7. If we look at what's left with the other one, 22 divided by 2 is 11. X cubed divided by x squared is an x, and we still have the y left over that we didn't take out.
We weren't able to do anything with the y?
Nope, they didn't have it in common.
Ah.
So we check our remaining factor. That is a prime factor, 7 plus 11. Nothing you can do there. Check by multiplying back in. You can check that in your head. Make sure you got the original polynomial. It takes about maybe 5 to 10 seconds to check in your head just kind of by multiplying. It takes a lot longer than that to make a fix if you get points off or anything, so it's worth it.
Absolutely.
Number 11, see that 15 common to both? That should be a red flag that at the very least you're going to pull a 15 out.
Definitely, that should be easy to do.
And then we see a B in common, so before we write that parentheses, let's put a B there. And now it's just a matter of making sure we have what's left over. The first one had an A. The second one didn't, but remember there's always that invisible 1 there.
Oh, I see. So this is just like the 9 in our example right above there,
Yep.
where when we divided out the 9, we're still left with the 1. And here we're dividing out the 15b, so that second term we're left with a 1.
Exactly. Number 12, we got a 3A and a 25B. Check 3 and 25. Nope.
Nope.
A and B.
Nope.
We found our second prime.
Dun, 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 dun.
Parentheses around there is a little celebratory. That's its own prime factor. 13, 12, and 27. 12 is even, but 27 is not, so no 2. 12 is 4 and 3, and 27 is lots of 3s.
Yeah.
So we know we can take a 3 out. X, Y, and Y.
They both have a Y.
They both have a Y. We end up with a 4x left over plus 21y divided by 3y.
Let's see, is that 27y?
Or 27y.
Yeah, okay. Well, it's still 9.
It's still 9. 4 and 9, they're both perfect squares, but that doesn't mean they have any factors in common. So I think we're done.
Yeah, I think you're right.
24, mn, and 16n. 24, we know we have a 2. Let's keep going up in multiples of 2. We know we have a 4.
Oh, 4 would be 6 times 4, and then 16 would be 4 times 4.
Can we have an 8?
Let's see, that would be 8 times 3 and 8 times 2. Oh, so 3 and 2 don't have any common factors. I think we might be done there.
Sure. We can't go up to 16 because 24 is not divisible by 16, but if we check an 8, we know that we took out a larger number, and that saves us some time. Mn and n, we just have an n. And pull that out, we have a 3m minus a 2.
It would just be a 2 because we already took the n out.
So look ahead. Let's see what's kind of different about these. We're starting to get to some trinomials, 3 terms. We have to check 3 numbers now, compare the 10, the 15, and the 20. You should be thinking 5s and 10s.
That's immediately what came to my mind. Except as far as the 10s go, I notice that 15 isn't divisible by 10, is it?
No. 15 is only divisible by 5, so let's take out a 5. If we pull a 5 out, then we have to check our z's.
Well, I notice that the last term doesn't have a z in it, so I don't think we'd be able to take a z out of every term.
Nope, so let's just take a 5 out. 2z squared minus 3z minus 4. And I will try to remember to cross z's because my students completely call me out for putting 2's and z's in the same problem.
You know, I've noticed that several of my students have actually made that mistake on their homework where they mix up a 2 and a z and they end up getting the wrong problem. Oh dear. Yeah, it's very important to have good handwriting, even in math.
Yes, something I never learned. So we look here, thankfully not too many 2's, but we see some 3's. We look at what our limiting one is. We only have a 3 there.
We have a 3 there, and we can't have any factors bigger than 3 because otherwise we wouldn't be able to take it out of the first term.
We also know that we've already used up our primes, so logic says we have to take a 3 out.
Yeah.
3z squared minus 4z minus 6. Maybe cross my z's. And I think we're done for now.
Yeah, I think you're right. Now, as far as 15 and 16 goes, I suspect that maybe someday we might find, because I've noticed up here that we've been able to factor trinomials before, and even in a previous section we had things like perfect square trinomials that turned out to be factored.
Sure. We can leave these as sort of a to be continued.
Yeah.
Because you know this chapter is going to continue with other types of factoring. Maybe some of you have done that kind of factoring before. Okay, want to take over?
Yeah, sure. Okay, so if I'm looking at number 17, I notice that as far as the number parts go, we have an 11, a 33, and a 44. And all those repeating numbers make me think of 11s first off. So 33, for example, is 3 times 11, and 44 is 4 times 11. And 11 is a prime number. So my first thought is, take an 11 out. And then I notice that all 3 terms have y's in them too, so I'm betting that I'm going to be able to take a y out as well. The only question is, how many y's can I take? I have 5 y's in the first, 4 y's in the second, and just 2 y's in the last. So I think the most y's I'd be able to take out of any of them is just the 2, because otherwise I wouldn't be able to take any more out of the third one. So I think what I'm going to be able to factor out is 11y squared. And I think what that leaves me on the inside, since I took out the 11 and I took out 2 of the y's, I'd be ending up with y cubed. And then the plus sign carries through. And then I'd have a 3 here, y squared. And then at the end, I took out an 11y squared, so I'd end up with just minus 4. So I think if I factor that correctly, I should get 11y squared times the factor y cubed plus 3y squared minus 4.
Looks good to me.
All right. Hey, I did one right for a change. Let's see if I can continue the streak. I notice that I have a 4 and a 10 and a 6, and that makes me think, okay, 2's, because they're all even. So if I take out a 2, and maybe I'll just write this for right now, I'll have a 2 there, but I also notice at every term, and maybe I shouldn't have written that parentheses quite so quickly.
That's why the eraser's beautiful.
Yes. It was almost made for mathematicians.
Yes.
I notice that each term has a u in it as well, at least one u, because my smallest factor here has just one u. So I'll take a u out as well. Let's see what I'm ending up with. 2u squared, I think, is what I get for the first term. Is that right?
Yeah.
Okay. And then 5u for the second term, and then plus 3. So then I'd have to check, because I wasn't sure, but 2, 5, and 3 don't have any factors in common, do they?
Nope, they don't have any u's either.
Oh, that's right. They don't have any u's. So I think I'm pretty much done there. Yeah. All right. Should I try maybe, we'll go back to the orange, just to make this fun. Colors are great. 9, 12, and 6. Let's see what we got there. And also m's, m's, and m's. So I'm thinking that whatever I take out is probably going to have some multiple that has 9, 12, and 6 in common. And I don't know if the word multiple is the right one. What am I looking for there?
I think a factor.
Factor is the correct word.
9, 12, and 6 should bring to mind some 3's.
Yeah, that's what I was thinking as well. So if I think about the 3, then this would be 3 times 3, 3 times 4, and 3 times 2. So yeah, I think 3 is the biggest factor that they would all have in common. Almost like a greatest common factor.
Almost like a greatest common factor.
Wow.
Wow.
Okay, and then I notice that they all have m's. How many m's can I take out? Probably, would you say 3?
Yes, the greatest number of m's.
The greatest number of them. Almost like a greatest common factor. Oh my
factor.
gosh, this is blowing my mind. Consider it blown. So here we have 3m squared plus 4m, and then I believe this last term is just going to be plus 2, and we should be done.
20 can look intimidating with the p's and the q's, but just again, if you see p's and q's, you may as well start writing p and q.
Sure.
Go ahead and write p and q.
Absolutely. We know that we're going to take either of those out.
You can always put an exponent in later. Look for your smallest power of p. I just see p to the 1.
Yep, right there.
Look for your smallest power of q. It's q to the 1.
Yep.
So next thing would be our parentheses, and just take those things out.
So let's see. If I take a pq out of pq cubed, that's just going to leave me with q squared, isn't it? And if I take a pq out of p cubed q, that's fun to say, I should just end up with p squared.
Yep, there's a little symmetry in problems like this, but we always try to catch you. Just take a little second, make sure you're okay. Okay, 21, 10, and 15, just like above. That should be, well, I'd say a 5.
I bet you're right.
And then a squared and a.
I think I can take an a out of there because that's the smallest term that they have in common.
Yep, b and b squared, also just take a b out.
Yeah.
And we end up with 10 divided by 5 is 2, a squared, a, and just an a left, and the b's cross out. 3, a's go away, and we just end up with a b.
So I can close off my parentheses, and we're pretty much done there.
Look at 22, compare it to 20. I see x's and y's and everything, so I'm probably just going to write an xy.
That's an excellent suggestion, yeah.
Can deal with exponents later. Check the x's, smallest one's a 1. Check the y's. If you look at the end there, we have a 1 as well, so take out an xy from everything, and we're just left with...
Well, let's see. If we take an xy out of the first, and we get rid of all the y's and just left with one x, and if we take out xy from the second, we're just going to be left with one y that we're subtracting. Oh, but here I notice that we take an xy out of an xy, and just like we have before, that would leave us with 1, because after all, we're dividing. We're not subtracting. If we were subtracting, you'd end up with 0, but here we're dividing, so you'd end up with 1.
So a good rule of thumb is when we take out greatest common factors, one of our factors should typically be the same style of polynomial that we had before. We started with a trinomial. We should still have a trinomial left over. It's just a little bit smaller in the sense of how it looks.
So if we have a 3-term polynomial up here, you're saying that we would probably end up with a 3-term polynomial down here. At least for now.
At least for now.
Because after all, we're just, right now, we're just learning.
Yes, we're just starting. Let's move on to the last four on this page. We're going to kind of blow through these a little bit quicker so we can get to some of the end stuff.
Right, so if you want to pause the video and give these four a try, if you're feeling really saucy, you can go ahead and see what kind of answer you end up with, and then we'll come back and take a look at those. I'm going to go ahead and turn the pen back over to Mr. Elliott.
Okay.
Because he is the master.
We're just going to go kind of quick here. So coming back from us, 6, 12, and 15, take out a 3. C cubed, C squared, and C, take out a C. D squared, take out a D. And we'd be left with a 2C squared minus 4C minus 5D. You'll notice I'm actually kind of thinking in my head while I do this because it's somewhat difficult to talk and write at the same time and kind of make sure you're doing this right. You guys would be the first ones to call me out if I mess this up. I'm going to switch to purple. 28, 42, and 56. Just think of 28 as 7 and 4. This is 7 and 6, and this is 7 and 8. I could start with a 7, but there's even a bigger number. I also know it's also divisible by 2. 7 times 2 is 14. So let's try taking a 14 out of these. We also have r's, r squared, then an s squared. So take that out, we end up with a 2r plus 42 divided by 14 is 3, 3, and then we'd end up with an s, and 56 divided by 14 is 4rs. So we're getting to some higher numbers here. I see 45, I see 15, and I'm going to try to divide that by 15, just for kicks. If I'm wrong, we can always come back to it. So I'm going to write a 15 down. I know I don't know the answer in my head. I haven't done this in a year or so. P squared.
I was going to be very impressed, Mr. Elliott, if you were able to divide 390 by 15.
Well, 315 is just a good place to try. And if we look at that, okay, let's do 390 divided by 15. Your grade school teachers would love to see that you can still divide long division. 2 is 30, 90, 15 goes into 90, 15 goes into 30 twice. So that would be 6. 6 times 15 is 90. 26. P squared minus 3PQ plus Q. And now I think it's important to say that we're really not going to let you guys use calculators much on this, and you shouldn't be using calculators at all when you're doing factoring. This is sort of important skills to be able to do this in your head, so just trust me on this. Avoid using them. 48, 64, and 24. I know we can take out an 8 out of all of those. And 24 divided by 8 is a 3. 3 doesn't go into 64, so let's just try an 8. 8 x to the third, y squared, and 6y to the fourth plus 8x to the third plus y to the third, or times y to the third, and then minus 3, and that'd be minus 3.
Yeah, it'd just be minus 3 because, after all, we took the x cubed y squared out of there.
Yep. Okay, 27, 28, 29, and 30. These are ones that what we call this is sort of, well, we have names for these. We have many names for these. I kind of like to see this as 3 times something minus x times something.
Oh, look at that.
In fact, you know what? I have an idea.